Okay, so before I get started with today's notes here, let's just do a quick recap of how you name basic things. If I were to give you a molecule that looks like this, let's go with 6 carbons in a row, and right here I gave you that. Hopefully you guys are pretty comfortable with this by now. 3-ethyl. Yeah, because you'd have to approach it as, hey, I found 6 in a row right here. So again, like when we name these new compounds today, you still find the longest group you have. Then you want to try to figure out like what your branches are. Since this is a branch of 2, you call it an like modifies it ethyl, and then because it's off the 1, 2, 3, you'd call it a 3-ethyl hexane. Now here's the rules for you guys. You are allowed to have tons and tons of the same functional group, but I can't give you more than one. So like either you're gonna get like iodides and chlorines like we talk about today, or you're gonna get double or triple bonds, or you're going to get hydroxyls, which are alcohols, or you're gonna get esters and ketones. But like you're supposed to just get one, and that's it. Okay. In theory, though, there's actually a priority system, so that if you have one of these and one of these and one of these and one of these, someone has to take like the number 1 spot and take priority. And I can't remember for the life of me how to figure that out anymore because it's been years since I went to organic chemistry in university. But like there is actually like a ranking system where like triple bonds always get priority or hydroxyls always do. Does that kind of make sense what I'm describing? But at the end of the day, like what we're gonna do today is rather than have like a hydrogen sitting right here, we're just going to change it out for a chlorine. And then on Thursday, we're going to talk about what happens if you have an OH group. And then on Friday, we're going to talk about what happens if you add one of those. And we're just going to add new things to it. But like I said, the naming scheme is like, it's the exact same. Once you get the hang of it, number it and say what it is. So, anyways, here's my opening slide here, just to remind you guys of what we should be able to name so far. I made this little like flow chart. So far, we've talked about anything involving carbon and hydrogen, and really there's 2 main branches. There's the aliphatic branch, where there's no benzene ring, and then there is the benzene ring branch. And why is benzene so popular? What makes benzene so useful? It has 6 different locations it can bond. Right? What makes carbon so useful? There's 4, right? And so in general, the whole reason why we're doing this is that carbon has 4 different bonding sites, right? And you can just keep going. You want to just add another carbon to the end? Go for it, right? You could have 2 carbons in a row. You could have 2 million carbons in a row. You could always add one more. That makes sense? What makes benzene so cool, though, is that this benzene ring right here really has 1, 2, 3, 4, 5, 6 different branching off points. And so that's why we have to kind of divide things into these 2 categories. And I think at first kids are perplexed as to like why would this need like its own branch, but like benzene chemistry is actually very common. Many different molecules have a benzene. So, and then this is really what we've covered so far: your single, your double, and your triple bonds, your benzene rings, and then we've also talked about how to do a branch. Okay, today, not tomorrow, we'll do a lab tomorrow. Today, Wednesday, and Thursday, we're now going to focus on how do we talk about stuff that doesn't involve just H and C. What if I throw in some nitrogens or some oxygens or chlorines and bromines? Okay, so today's topic, we're going to talk about, first of all, what are known as the organic halides. We're going to keep it simple. Okay, what makes something organic, by the way? Yes, but there's actually some exceptions. I didn't teach you guys this lesson. Mike was doing this lesson because I was sick that day, I think. There are some exceptions. Maybe I should point those out again just in case you've forgotten. Organic means that something contains carbon, so contains carbon with the exception of, do you guys remember the exceptions? Carbon oxides, like carbon monoxide. Okay. Board just died. What was that? Yeah, if it has an ionically bonded thing, it doesn't really work. Maybe I should just revise the list here. It's in your notes, by the way. You can't have carbonates. So if it has a CO3 in it, like say CaCO3, that doesn't count. If it's got a cyanide in it, it doesn't count. And if it's got a carbide in it, it doesn't count. So if I give you like NaC or something like that, those don't count. So the 4 exceptions are carbon oxygen, like carbon oxides. The main 2 are carbon monoxide, carbon dioxide. Those don't count. Carbonates, cyanides, CN. So, like for example, KCN, potassium cyanide, that wouldn't count. And carbide, where like carbon is the second of two things ionically bonded. That's your list of exceptions. Otherwise, what Rebecca said works though. If it contains carbon, it's organic. What is a halide then? Well, a halide is something that involves a halogen. So you guys remember the halogens, right? Your main four are chlorine, I should start at the beginning. Fluorine, chlorine, bromine, and iodide. Those are your halogens. What makes halogens so reactive? Yeah, they want one electron. And not only that, but like they're pretty good at fighting for it. You guys remember electronegativity? All of your halogens want one electron. If I could just write that down here, they want one electron, and they have a relatively high electronegativity, which means they're pretty good at getting that electron. Here's really what happens then. These things are basically like an upgraded version of hydrogen. Let me say that again. These things are like an upgraded version of hydrogen. Because how many bonds can hydrogen form? Well, also one. Does hydrogen want electrons? Yeah, not bad. But like fluorine and chlorine are actually kind of better at wanting electrons than hydrogen is even. I believe electronegativity wise, hydrogen is 2.2 and fluorine is 4 and chlorine I think is 3.2. So like in general, what's going to happen you're going to discover is that these molecules here, they're going to take the place of hydrogens. Now before I get too far on that, I want to talk more about the idea of a functional group. A functional group is basically like an arrangement of atoms within a molecule. It's something like special or unique that comes like in a grouping. I'll show you some I've already done before. This right here would be a functional group. That'd be a chlorine functional group, an organic halide. This is called a hydroxyl. We'll get to that another day. This is called a carbonyl. Also get to that another day, right? But like those groupings of atoms mean something. There's one that goes like NH2. That's either an amine or an amine. I always forget which one is which. But anyways, you guys get the idea. Is like this is like, I don't know. You guys know like the Mr. Potato Head dolls, where you can like take off one set of lips and put on another one. It's kind of what I think of when I think of these. Or like what I'm really doing is there used to be a hydrogen right here, but if I want to rip off the hydrogen and put this thing there in its place, that's a functional group. So all we're doing is we're taking off the hydrogen end cap attachments, putting something else there. Here's actually a diagram I found online that kind of helps with some of the functional groups we'll learn about. Now, I need you guys to know that I'm going to show you all of these ones here, just because that's who I am. But on the diploma and on your tests, you're only required to know this one, this one, this one, and that one. So if you guys want to, actually no, you don't even do ethers, so I take that back. Okay. I'm going to show you a lot of them, just because once you learn how to name these little groups here, it's really all the same. But in terms of the diploma exam, make sure I have it right here. You guys need to do alcohols, carboxylic acids, esters, and I guess I can throw one more here. The, what did I just call them? Organic halides, which is RX. Okay, so that leads to the first question. Chris, what the heck is R? R is not a compound. There's no periodic table for R. Anyone want to take a stab at what R refers to? Any guesses? Say that. Say that. Yeah, it's an undetermined carbon chain, basically. If you want to write that down, I won't write it out here, but R refers to an unspecified, there we go, carbon chain. Because you know how you can have one carbon in a row, or two, or three, or four? That R right there just implies that there's a whole bunch of carbon and we don't actually care how much there is. So if you ever have something that looks like this, as an example, carbon, carbon, kappa with OH, that's an alcohol. An ether would go carbon to carbon to carbon to carbon to oxygen to carbon. And it could have 4 on one side and 1 on the other. It could have 2. This could even have a branch if you wanted to. We do one or the other, by the way. We don't do like multiples. You either get one functional group or you get double bonds or you get branches. But like we don't throw multiples in usually. So anyways, I'm going to show you all of these if that's okay. But I'll let you know which ones are being tested on. So this is probably one of the things we're going to spend a lot of time talking about here. Functional groups contribute to physical properties. Um, we talked last week, goodness, what was it, Wednesday maybe, about crude oil. I had a long lesson on basically the petrochemical industry, especially in Alberta. And one of the things I talked about was fractional distillation. Do you guys recall the term fractional distillation? What's the point behind it? Yeah, I like the word separate. Really, that's the key, right? You've got all these different types of hydrocarbons. You want to separate them. And what do we separate them based on? Boiling point. Yeah, that's mainly the main idea here. Well, that's what I want to talk about as we learn each of these new functional groups, is that they control key characteristics, including bonding strength. Now, a quick review that we learned from Chemistry 20. There are three things that hold molecule A and molecule B together. You guys remember the terms inter and intramolecular bonding? Intramolecular bond is what keeps this molecule stuck internally. Intermolecular bonding is what makes these two things stick together, and the more bonding it has sticking them together, the higher the boiling point. Okay. So the three main things that affected that were London forces, which basically were bigger is better. If you have methane and you want to compare it to ethane, ethane has a higher boiling point. Want to compare it to propane, propane's higher, which kind of makes sense then, because you guys probably know a little bit about these gases. Propane is what you'd use in your barbecue, like outdoor barbecue. Propane, big, white canister, right? It's a gas. Butane is one higher. Butane you'd get like in a little lighter, and you can actually sometimes see like the liquid butane swishing around inside. You upgrade that from butane all the way up to octane, which is what you guys put in your cars as gas, and that's clearly a liquid. If you keep going all the way up until you have like, I think it's 20 or so carbons, then all of a sudden it starts to be more of like a solid consistency. Like, for example, candle wax, I believe is C20H52. Could be wrong on that one, but it's somewhere in that one. Maybe it was 26. Anyways, as soon as you're starting to get to the 20 for carbon, now it's solid. Why? London force. You guys recall that? Okay, 2. The second thing that causes things to be sticking together is dipole forces. Basically, if you have a molecule that is like lopsided somehow, the electronegativity differences cause them to be able to stick together. In essence, symmetry is actually bad. If everything in the chemistry world was perfectly symmetrical, nothing would stick together. But if you had a chemical that looked kind of like this one right here, where there's two things on one side and there's this lopsided functional group, well, now put a second one together, and these things will actually stick to each other due to polarity, kind of like magnets. The third thing is by far the strongest. It's called a hydrogen bond. What's wrong about calling it a hydrogen bond? Yeah, because it's more of a force of attraction. A hydrogen bond is where you have either oxygen, fluorine, chlorine, or nitrogen. It's attached to a hydrogen, and that hydrogen is so stripped away of its electron that really it's a proton, right? The other element in that internal bond, I should maybe draw this out. This is important review before we move on. If I were to give you, say, N, H, 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 like a lone pair here, what ends up happening is this hydrogen right here, they share the electrons, but they really don't share them. What ends up happening is this nitrogen right here, it has almost completely stolen the electrons entirely towards it right here, and this hydrogen here is a positive. Now, is that on its own enough to make a molecule have a hydrogen bond, though? It has to have a lone pair somewhere. The good news is there's a lone pair right here. So if I were to have another molecule just like it, what can happen is this proton can attract one of those electrons, and that's the hydrogen bond. Do you guys remember a little bit of this? Okay. We're going to talk about that a lot over the next couple lessons, because as we're getting into functional groups, like I said here, we need to talk about their chemical and especially their physical properties being boiling point. One of the most challenging questions you're going to get in this section is one that you've already kind of done a little bit. I prepped you for it in Chem 20, but it's the rank the following compounds based on boiling point. You guys remember doing that on your Chem 20 quizzes? I'd give you 4 numeric response compounds, and you have to figure out which one has the lowest boiling point all the way up to the highest boiling point. So you have to know how these things compare to each other. Okay, anyways, let's move on here. Let's talk about the organic halides. The basic concept here is it goes Rx, meaning R is a whole bunch of carbons, and then X is some sort of halogen. So any of the four: fluorine, bromine, iodide, and whichever one I missed. You guys know the four. Bit of context before I get on to naming these. These are actually really commonly used, and you've probably heard of some of these ones right here. The chlorofluorocarbons. Anybody ever heard of those before? What were they used for? Say that? Yeah, refrigerants. What were you going to say? Yep, same thing. It's basically the same concept in different ways. Back in, oh goodness, I want to think 87, there was something called the Montreal Protocol, which basically tried to phase out these chlorofluorocarbons. Do you guys know what they were doing that was harmful to our environment? Yeah, these things eat away at ozone. And so they were starting to put holes in our ozone layer. I think I even posted a Science and Society reading talking about how there was some success now in that, and how that may have actually masked global warming. Anybody read that article? Okay, you did. Anyways, those are chlorofluorocarbons involving carbons as well as Cl's and F's. And we use them in so many different things. I mean, from things like a DDT, which is basically used to try to like get rid of pests and bugs, to like Teflon. I don't know why there's an extra A there. You guys know what Teflon is? You use it on like frying pans. It's like a non-stick surface. Okay, let's talk about, before we name them, let's talk about some of the properties, because I need you guys to know that. These things, they might be non-polar, but they're more likely to be polar. And the reason why is that there's going to be like an uneven, unsymmetrical part to this. It's possible that they could be symmetrical, but it's more likely that they're not going to be symmetrical. And you'll see it as soon as I draw a few. And because of that, they're going to have higher boiling points than similar hydrocarbons. Let me come back to that once we name some. Okay, find this slide here. It's only 2 away. I'm going to give you a name. Let's try to draw it. It is a 2,2,5-tribromo 5-methylhexane. Start at the end of the word. Hexane means you need 6 in a row. So 1, 2, 3, 4, 5, 6. On this one, this functional group takes priority. So that's why the 2, the lowest number we have here, goes for a bromo. So basically pick an end to be your 1, 2, 3. Like, I'll make this be 1, that'll be 2. So on this one here, I need a bromine. But there's 2 2s, so a second bromine needs to go this way. Is it possible for there to be a third bromine? No, it wouldn't even make sense, would it, right? And then on, let's see, that's 1, 2, 3, 4. On the 5, we need another bromine. And on the 5, you also need a methyl group. I'll just draw like that to save some space. Okay. This is a 2,2,5-tribromo 5-methylhexane. Now, one of the things I often skip is drawing out all the hydrogens. So if I were to draw out the remaining hydrogens, let's use that as a line there. Can you guys kind of see what I was referring to as like the bromine is effectively taking the hydrogen's place? Right. Normally, every one of these attachments around the edge here would have been a hydrogen, but just bromine's taking its spot, that's all. That means 2 things. First of all, it's going to have higher London forces. Say that one more time. It's going to have higher London forces. Why? Bromine is much heavier than hydrogen, right? Remember London forces? London forces are basically bigger, better, right? How many electrons would a hydrogen contribute? 1. How many hydrogens does a bromine contribute? Like 35? A lot more then. Does that make sense? So 1, this thing has higher London forces. So I would expect this to have a higher boiling point than just like a regular old hexane. If I were to compare a hexane to this thing right here, this thing must have a higher boiling point. But also, it's probably polar as well. Because unless this thing is like perfectly symmetrical, there's going to be a dipole to it. Now, I don't really care where the dipole is, but can you guys agree that this thing is not perfectly symmetrical? No. It's not. And even if like this one right here, by the way, were a bromine, that still doesn't necessarily count. Because keep in mind, although we're drawing this in 2 dimensions, in 3 dimensions it actually has to go like carbon up to hydrogen, out to hydrogen, one of like these guys. And we're doing like those lines like this. So like as soon as you have to start drawing it with like these lines here, it kind of screws things up. So unless it is perfectly symmetrical, it's probably going to have a dipole to it as well. Now, there is an exception. For example, this molecule right here, if I were to give you, say, 2 carbons, and you know how there normally would be 6 attachment points? Hypothetically, let's say that I had like a couple of them as hydrogens, and then these ones as chlorines. Okay, that would be polar. There's no way that balances out. But what happens if literally every single one was a chlorine then? Now it would be symmetrical. Then it would not be polar anymore. You guys see that difference there? So like if you had, just to compare here, if I had 2 carbons and I had 2 hydrogens here and then a bunch of chlorines here, if I were to ask you to compare these guys' boiling points, this one would be higher and this one would be lower. And the reason why is that this one here is not symmetrical, and this one here would be perfectly symmetrical because everybody's got a chlorine. This one would have more London force, but London force doesn't really compare compared to a dipole. And a dipole doesn't even compare compared to a hydrogen bond. So we're going to really pull on that unit a lot this next little while. Did that make sense? Just because, why don't we try naming these compounds here? What would you name this guy right here? Let's start at the end. What would the end of the word be? How many carbons do you have? Okay, so we call it an ethane. How many chlorines do you have? Okay, so that's a hexa. And then you'd call it a chloro. You'd call this hexachloroethane. Would you need numbers? Why not? Everything gets used, right? So there'd be no need for numbers. However, this one I drew down here would also be known as a chloroethane. Only we didn't use 6 chlorines. This time we used 4, so what is 4? Tetra. However, this time we do need numbers because it depends on which ones we put them on. So I'd probably have to go with a 1, 1, 1, 2 tetrachloroethane, which kind of implies that 3 of them are on this one, and then 1 of them is there. Because in theory, I could have done 2 here and 2 there, which would have made it a 1, 1, 2, 2. Follow that? Okay, let me go back to the slide I skipped here then. Basically, the missing piece then is all you do is at the beginning of the word, you add in a either fluoro, chloro, bromo, or my personal favorite, iodo. It's fun to say. Iodo. Right, that's all you got to do. You still have to number them if numbering is necessary, and that's it. Now, I have to relook up the rules as to what you guys are expected to be able to do, but I think you're supposed to be able to do branches along with these functional groups, but that's it. Okay, but I'm going to show you guys how to do much more than what's the diploma requirement because I want you guys to have a good basis for this. But yeah, basically the idea is you either get one or the other, though. So let's try this one. Try to name this guy. So start at the end. How many carbons in a row? 1, 2, 3, 4, 5, 6, 7. So that's a heptane. And if we had to, I'm sure we could deal with a double bond there. But I'm pretty sure you're supposed to get one or the other. So this will be a heptane. We need to give it the lowest numbers possible. So hopefully that's obvious. You got to start counting from this direction here. We still go alphabetical though. So the 2 bromo, then the 4 chloro is the name. On the 2 you have a bromo, on the 4 you have a chloro, 7 in a row. The 2 is not first though, because 2 is numerically first. The 2 is first because bromine is alphabetically first. Fair enough? Okay. Let's try this one. Try to draw me a dichlorobenzene. But there's actually 3 different isomers I want you guys to be able to draw. What would a dichlorobenzene look like? Benzene looks like this, right? I'll draw 3 of them because want 3 different ones. Again, what's unique about benzene? 6 launching points, right? So I guess in theory you could have a chlorine here and here, right next to each other. You could have a chlorine here and there. So what would this one be? This would have been the 1,2 dichlorobenzene. This would have been the 1,3 dichlorobenzene. But if I went with top and bottom, that would be the 1,4 dichlorobenzene. Anybody want food? Pause for a sec. I see muffins, cheese strings, yogurt. I'm sure there's fruit in there somewhere. Anybody? We're good anyways. Thanks so much, guys. Why can't I have a 1,5? Yeah, in a way, right? Let's say I tried to have a 1,5 dichlorobenzene. This is a really important moment. So here's the same thing. I want to go on the 1, 2, 3, 4, 5. So I put that over there. But isn't that the exact same thing as this one right here? Only like flipped around? If you look at it from the other direction, it's the same molecule. So that's why there's only 3 isomers available here. Does that make sense? Like if I were to literally go stand at the board, if I look at it from this direction here, the chlorine's on my right. But if I could like stand behind the board and look at it that way, it would be on my left. You know what I'm saying? So it's the same molecule, just flipped around. Okay, so now that I've kind of given you guys the basics, that's really all you need to know how to name it. Why don't you guys take 5 minutes here? Try naming these ones. Maybe you've already beat me to it. So after you guys do this, I still need to talk about how to make these molecules. The second half of the lesson has to be about the reactions. But I feel fairly confident that you guys are going to do pretty well at this whole naming thing, because it's not really that much different, hey? Quick reminder, just because you see a hexagon doesn't mean it's benzene, by the way, right? If there's no circle in the middle, it's a cyclohexane. There is a difference. want to talk through a couple of these because I threw a couple of interesting ones up there. But take a look at my answer. You can read them well enough if you get a chance to see what you have, what I have. One thing I do want to make sure I'm clear on though, you still need to give lowest numbers where possible. So the lowest numbering scheme is still the most important. When we eventually work with multiple things, like if we do bromines and hydroxyls and double bonds, then there's a bit of a priority system of things. But we don't need to really worry about that yet. So just give things as low of a number as you possibly can. Can I talk through a couple of these? Or you guys want a few more seconds to process? Okay, so this top one right here is hopefully pretty straightforward. So this top one up here has 1, 2, 3, 4, 5, 6, 7 in a row. The lowest numbering scheme is most important though. So you could either go 1, 2, 3, 4, 5, 6, a 3 and a 6 branch, or from the other direction you could go 1, 2, 3, 4, 5, which is why I went that way because a 2 and 5 is better than the 3 and 6. Okay, and in terms of first, bromine is alphabetically before methane or methyl groups, so that's how I got the 5-bromo-2-methylheptane. Does that make sense? But again, in the future, we'll eventually get to functional groups that take priority as to which side is which, but that doesn't really matter to us until we get to that point. So, this one right here is a very similar scheme then. You can either start counting around the circle, and I think the lowest number pop combination you can have is to go 1, 2, skip 3, and 4. I mean, you could go 1, 2, 3, 4, but 1, 2, 4 is better than 1, 3, 4. So I'm going to start here with a 1, 2. That's where the dimethyl came in. By the way, don't forget the word di. It's little. I don't see that being something they would test you on, but that'd be so rude if it was. But don't forget that should be a dimethyl right here. 4 on fluorine, and then it's a cyclohexane, not a benzene ring. So, okay, this one down here I want to talk about for a bit. The trickiest part of this one is figuring out that this carbon right here, that's a 1 written by there, right? In terms of knowing how many carbons to fit in a row, you could go like 1, 2, 3, 4, 5, 6, 7 and count that last one down here. That doesn't work though. And the reason why you can't go 1, 2, 3, 4, 5, 6, 7 and count this as your main branch is that this chlorine then wouldn't be on your main branch. And so it's kind of another rule that you need to get the carbon chain that is the longest, but that also contains all of your functional groups. And so that meant that I actually had to go 1, 2, 3, 4, 5, 6, 7 and go up to this one right here. Because if I take this like kind of chain right here, now every functional group is on the main path. Okay. I mean, eventually, if you do this enough, you'll have to have functional groups off of functional groups. And like you can imagine, like if you can imagine it, it's probably possible. But at least for right now, try to make sure that the main pathway contains all the functional groups. So based on that, then the lowest numbers, we're starting up at this carbon right here, 1, 2, 3, 4, 5, 6, 7. Off the 1, off the 2, and off the 6, you have chlorines, hence the 1, 2, 6 trichloro. Chlorines alphabetically first. Then on the 1, 2, 3, 4, right here, there's a little ethyl group. And then on the 2 is where that methyl group goes for the heptane. First of all, did that make sense? Any of you get that? Okay. Did you do what I was originally pointing out at first? We do like these 7 in a row, and like that was your last one there? Okay. Does that make sense, though? The reason why that can't work is that how the heck do you name this chlorine? That chlorine is actually hanging off the methyl branch then. So it's actually possible. Let me draw one out here. I'll do something really extreme, but I think I've seen one of these ones before. They really tried to mess with you where you could go like this. Let's see. Let's say that was the molecule there. A lot of people, when they look at this one here, here, I'll do it like that to make it extreme. They would say, how many carbons do you have in a row? And they would say, this is how many carbons you have in a row, so they call it a heptane. But the problem with that is that your chlorine is actually not directly attached to that. So the most amount of carbons you'd have in a row then would be these 5 right here. 1, 2, 3, 4, 5. And then this is a propyl group hanging off instead. So you'd actually name this as like a 1-chloro. See a chloro 1, 2 propyl. And then 5 in a row would make it a pentane. So, anyways, that's why I wanted to point that one out. It's a good learning moment. Okay, other noteworthy ones. This one right here is pretty straightforward. We don't even need a number because literally, if you wrote it out, there's 3 hydrogens and 1 bromine. We don't even need a number. It's all definitely off the 1. So, this one right here, though, does need a number because you could have attached the chlorine off of any of these 3 carbons, and specifically it was off the 2. So you do need the number here, not there. This iota one, though, the cyclohexane, really doesn't really matter. Whichever one we're picking it from, it would be the number 1 molecule. So that doesn't really matter. And then for the last one here, I think I counted lowest numbers 1, 2, 3, 4, 5 going this direction. 2 of them on this and 1 over there. So don't forget the dimethyl, though, because there's 2 different methyl groups. All right. That makes sense to you guys? Okay, second half of our lesson then. We need to talk about how to make these. We're going to do this in a lab tomorrow. Like I said, tomorrow's lab's pretty boring. You'll actually have a lot of time tomorrow. So if anybody, do you guys need more time to work on that quiz, by the way? Yeah, okay. So I'll probably give you some time today, but tomorrow would be a good day as well. Basically what we're going to do is 2 different reaction types. One is known as addition, one is known as substitution. And we're going to test the length of time it takes for them to occur and basically how well they react. But it's boring. It literally is combine chemicals together, let it sit for an hour, and go back and look at it. Okay. So anyways, the 2 reactions I want to show you, the first one is addition. And I've already kind of shown you this concept. The idea of addition is you take an unsaturated hydrocarbon. What does unsaturated mean? It's not full. Unsaturated means it's not yet full. Full of what? Yeah, of hydrogen. For example, if you have this molecule right here and there's hydrogens everywhere, is there room on it? No. It's completely filled up. But if I were to give you almost the exact same molecule, add a double bond, the bottom one is not yet full. There's room right there, and we can add something to it, hence the name addition. Right? Depending on what we add to it, depends on what you make. Now, I've already shown you this in a previous lesson. If I add hydrogen to it, we call it hydrogenation, and basically you're now saturating a molecule. So if you were to add H2 gas to it, 1 hydrogen takes each spot, and now it's filled up. Well, because what you're going to do is you're going to break the double bond, though. Okay, sorry, that wasn't clear. Break the double bond, and because keep in mind, a double bond is basically just extra electrons, right? So all you do is you take the extra electrons that are right here, add 1 of them here, add 1 of them here, 1 hydrogen attaches to each, and now it's full. The question is, well, what should we add to it? If I just add hydrogen to it to fill in those slots, that's kind of boring. But what if I were to add, well, that's actually what this slide here is. Okay. So just to reiterate the point, I've already shown you this before. Bust up the double bond, put a hydrogen here and here, you've now saturated a molecule. But what if I don't add hydrogen? What if I were to add HCl? Well, if I were to add hydrogen chloride or hydrochloric acid, all of a sudden what would happen is this is an H and this guy right here is a Cl, and guess what we just made? We just now made a functional group of like the organic halides. Now, what if I were not to add HCl? What if I were to add ClCl, which would be like chlorine gas? Well, now, both of them go there. So it really depends on what you add, as well as how long you let it react for. There's a couple different conditions we'll talk about. But yeah, that's how you get a chlorine in the place of a hydrogen. You literally take a molecule that wasn't quite fully built yet, and you just make the last building block be something that involves a Cl. So you're talking either adding like bromine gas or HBr, or adding chlorine gas or HCl. Not that you'd ever do this, because it's like terrifying stuff, but you could use fluorine gas. That's what Mike, did he tell you about his work with fluorine? Oh, he worked with fluorine at the university. It's scary stuff, because it's so reactive. Hydrofluoric acid is like one of the most dangerous acids we know of. It's what they used on Breaking Bad to like dissolve the bodies. Remember that? Yeah. It's like potent. Anyways. Okay, so here's basically this slide here talking about what I mentioned there. If you were then to take ethene and add chlorine gas, or just some sort of liquid chlorine if you could get it in that format, what would happen is both of these two open spots here would now get filled. The double bond would break up, make a single bond, and you now have a 1,2 dichloroethane. Right? So pretty easy concept, right? All you got to do is just have an unsaturated, add something to it. This is more pictures of basically the same thing. I'm going to picture you to death over the next little while. Here's an ethyne with a triple bond. If you added a single bromine, all of a sudden you'd fill in 2 slots. Well, what if you left it for a long period of time and you added more bromine to it? Eventually you could fully saturate the molecule. And that's one thing we're going to discuss as well, is that if you left this for 5 minutes, you might get one of these. But if you left it for 10 minutes, then this spot and this spot could get filled out too. And so time is one of the biggest indicators, because the longer you leave it for, the more saturated it would be. Does that make sense? So, because really what's happening is 2 reactions. This goes to here and here, and then this guy keeps finding more of the bromine that's lying around, let's call it this one here, and further saturates it. So. Now, a third thing you need to know about, and this is one of the questions on your lab tomorrow, is about the concept of isomers. If you guys recall, isomers are where you have the same stuff, but in different orientations. I already talked about Mr. Potato Head, actually. That's a good analogy. If you were to take his eyes and his ears and pop them off and put them in other spots, he looks funny, but like he is still Mr. Potato Head, just with different orientation. One kid years ago actually gave me the analogy of Transformers. Did I use this one with you guys already? Where like you have a pickup truck, and then you have Optimus Prime. And at the end of the day, it's supposed to have the same stuff, except in the movies, like somehow he's like a truck, and then he's like 3 stories tall somehow. Clearly, law of conservation of mass was broken. Anyways, sorry. Chemist goes off on a rant. Anyways, but the same stuff's supposed to be there, right? Just in different orders. That's kind of what happens here if you add hydrogen halides. If you add a hydrogen and chlorine, it's about the orientation. Okay? Imagine that you've got like Lego blocks that you need to kind of like fit together. And this one right here is not symmetrical. I could either put the hydrogen here and the chlorine here and fit it together in that orientation. That would produce this molecule here, a 2-chloro, because chlorine's on number 2. But what if you took this thing right here and you flipped it around so the hydrogen went here and the chlorine went here? If you literally just flipped it. Then when you slotted it in, well, now the chlorine would be on the 1 branch. And so what ends up happening is there's a little bit of actually math and probability to it. I would expect 50% to be this and 50% to be this, as long as there's like an even random chance as to how the hydrogen and chlorine would like slot into that spot. You get what I'm saying there? So it's it is actually not only likely to create isomers, it's almost an absolute guarantee. And so you'd have to actually find a way to separate these 2 things here. The good news is that they are not exactly the same, and so they do have slightly different boiling points. This guy right here, I bet you is slightly more polar than this one right here, just due to the location of the chlorine. This chlorine is like off on the end cap one. This one's kind of buried in the middle. Right? And so this one just might have a slightly higher boiling point. That's how you'd separate them. Let's try an example here. I want you to react acetylene, which is just the common name for ethyne with a triple bond. Anybody know what acetylene is used for? Welding. Use acetylene as a welding agent. It's C2H2. So it's a single carbon with a triple bond. And because of that, you've got just 2 hydrogens kind of capping the ends here. That's what acetylene is. Acetylene is highly reactive. Why is acetylene highly reactive? Yeah, it has a triple bond, which means that there is like open slots for something to come in and like, I don't know, dock. If you kind of imagine like a Star Wars kind of concept here, right? A ship can come in and dock right on this side right here and on this side right here. We're going to use hydrogen chloride. which means that this can happen a couple of different ways. If I were to add a hydrogen and a chlorine here, it would then give me this molecule here, H to C to double bond to C to H, and you'd have that one there. We've now created a chloroethene. Now, hypothetically, let's say that I change these two things around. Would that make a different molecule in this example, though? What if I were to have had the hydrogen and chlorine flip around, and so chlorine goes here, hydrogen goes there? It would make this molecule here, chlorine to hydrogen. Are these two molecules actually different? This molecule here and this molecule here, if I change the order of the HCl, is it different? No, because I've just flipped it around. So sometimes isomers get created, but if I were to flip, that's why I have like an arrow here for this. If I were to flip around where the H and the Cl go, if I go H then Cl, or Cl then H, in this example here, I don't think it actually matters. And we've now created a chloroethene. Why does chloroethene not have a number attached to it? Because it really doesn't matter. Right? In this one right here, I guess you're the carbon with it's the number 1. Over here, I guess you're the carbon that's number 1, but it's still the same molecule, right? Now, hypothetically, though, let's say we kept reacting it. So let's say we took these two molecules here. So I'll redraw them again. And this one here. H to C to C to H. And then we'll go H and Cl. Okay, so here's the two different ways we drew it. But we know that's the same molecule here. What if I kept adding more hydrogen chloride to it? Well, now I could get isomers. Because what if I went hydrogen and chlorine in this orientation here now? If I went in that orientation, see how the chlorines are on opposite carbons? This would make it a 1,2 dichloroethane. But what happens if it was added in this order here for the second one? Hope you guys kind of see what I'm trying to hint at here. Depending on that orientation, now, if they both slotted in the exact same way, now you'd actually have a 1,1 dichloroethane. Here you'd have a 1,2 dichloroethane. And really, we can't control exactly where it reacts. There's entire courses you can take on chemical kinetics, which is basically about the what is happening when things react. And at this point here, it's really just probability. We're going to assume that half the time it would make one of these and half the time it would make one of those. But these guys are considered isomers of each other because now these two guys are on opposite carbons and these two are on the same carbon. Make sense? Okay. Boy, second reaction that can take place. This one is not nearly as effective, but it will work. And we're going to hopefully see this in our lab tomorrow. It's called substitution. Addition makes sense. Literally, there's an open gap, and you just add something to it. It just slots right in. It's like when Kinsey builds with Lego. She just puts the last block in place. We're good to go. Substitution is more like she builds her structure, and she discovers, nah, I don't really like having that red block there. I'm going to take that red block off, and I'm going to put a black one in its place. I don't know if this makes sense to you guys, but sometimes I have to remake Kinsey's Lego structures, and it's supposed to have a black 2x2. But the black 2x2 has been lost, and so instead I decided to put the red one in its place. I know it's not the right color, but at least it fits, right? And then later, we finally find the black 2x2 piece that was supposed to go there. So what do? I go take the old Avengers ship that I made for her. I take the old piece out, and I put the new one in. That's substitution. Here's how that looks here. We're going to take a saturated molecule here of propane. It is completely full up. There is literally no spaces to add bromine. And what's going to happen is like the old switcheroo. So this hydrogen right here, we're going to rip it off. And what's going to happen is this bromine is going to take its place. And so you guys can kind of see how right here, this bromine right here is now one of the bromines is in that hydrogen spot, and this hydrogen came off, which means you have a byproduct of HBr. Because really what's happened is this H is now going with this Br right here, and this Br right there is going with that carbon in that spot there. However, how do we know which hydrogen is going to get replaced? We don't. Which is why this has been written kind of funny, because it could rip off this hydrogen right here, which would make it a 1-bromo. If you ripped off this hydrogen right here, it would also be a 1-bromo. This one, or this one, or this one, or this one. If you ripped off any of those hydrogens to play the old switcheroo, it would be a 1-bromo molecule. But what happens if it rips off this one here, or this one here? Then it becomes the 2-bromo. So you're going to create isomers, I guarantee it. Which one are you going to create more of, though? The 1-bromo or the 2-bromo? Probably the 1-bromo, because it's more likely. Right? In a way, there were 8 hydrogens to rip off here. 2 out of 8 of them, or 25% of them, will probably turn into a 2-bromo. And 6 out of 8, or 75%, would have resulted in this one. It really depends on which hydrogen you rip off and play the switcheroo game with. Right? Since there were 1, 2, 3, 4, 5, 6, 7, 8 logical choices, it just depends on which one it is. But again, it's going to create isomers. But this time, I don't think it's going to be an even proponents. I would expect to find 3/4 here, 1/4 here. At the end of the day, though, if I were to write this in a chemical reaction, the reaction looks like this regardless. Right? What you had was 8 hydrogens, and then a hydrogen and a bromine did the old switch game here. So now 1 hydrogen is now with the bromine, and there's a bromine attached to this guy here. But this is one of the downfalls to writing it like this. What does this tell you? Does it tell you which one of the carbons the bromine's attached to? No. I have no idea whether it's attached to the 1 or the 2. Right? So that's why writing it like this is a little bit disingenuous, because when we first taught you guys how to write chemical equations, you probably never considered, well, where is the bromine? You just looked at this and said, hey, it's balanced, we're good to go, right? But now there's more to consider. What sort of structural isomers could be created? So, most important thing I need you guys to know, it is always a 1-for-1 transfer. What does not happen is both bromines both getting attached and then ripping off hydrogen gas. That is not how this works. Substitution is an exchange, 1-for-1, not 2-for-2. Okay, same thing can happen with benzene rings, by the way. Is benzene saturated? Yeah, benzene is considered full. I know there were 6 attachment points, but there are, in theory, 6 different hydrogens sitting around on the outside here, which means there's 6 different hydrogens that can change out with the chlorine. One of them will, by the way. I don't know which one. It really doesn't matter. They all have equal odds. And honestly, if any of them change, it doesn't really make a difference because it's a 1-chlorobenzene. All of them get number 1. But yeah, just don't forget that you can do this with benzene. Can you do an addition to benzene? No. Benzene does not have open gaps on it, but you can substitute. Here's what I need you guys to know for tomorrow. Don't worry about the benzene so far, but focus on this. This is very slow. It takes a long time to do this because you literally have to do 2 reactions. You have to rip off the hydrogen. You also have to split apart your diatomic. You then have to put 1 in that spot and 1 in that spot. There's a lot of bond breaking to take place. And so what we're hopefully going to see tomorrow is that this reaction will take an hour to do before we can finally see something about it. And the way we're going to see it is I'm going to set it up so there's some color changes taking place. And so hopefully what we're going to see is that the addition reaction takes place almost instantly, and that this reaction takes place slowly over time. Often you need to use light. You guys remember what you call it when you put something over top of an arrow? What we're referring to is when you have to put something. Yeah, that's it. Catalysts actually get used in multiple units here, but we often need to use a catalyst to make this take place a little bit faster. It will happen, but if we're going to see this happen tomorrow, we're actually going to use ultraviolet light. So I've got a couple of UV lights that we'll use to shine on these things, and hopefully that'll make it so that within the hour we can see something. Okay, that's all I've got. I think I just have a summary slide here. So here's what we've covered today. You guys should now be able to name your first functional group, which is basically just add a chlorine, bromine, iodide, or fluorine in the place of a hydrogen. What does it do to the molecule's properties? It's going to give it a higher boiling point. One, because it's got higher London forces, and two, probably because it's making it polar. Right? We're eventually going to talk about oxygens and nitrogen functional groups and how those rank. But basically, our ranking system is your regular alkanes go here, and if it's got a chlorine bromine iodide, it's slightly higher. How much higher, we really can't say. We just know that it's higher. Okay? So you should know how to name them and draw them, and now we've known two reaction types. Addition reactions happen to unsaturated molecules. That means they have to have a double or triple bond. And you either add a completely perfect diatomic like chlorine-chlorine or bromine-bromine, or you can add HBr or HCl. When you add the HCl, though, depending on which way it slots in, can make isomers. So you got to be careful that you're aware of that, because it does make a difference. So that's addition. You can also make these things through substitution. If you want to do it through substitution, it has to be made with the diatomic one, though. It has to involve like a chlorine-chlorine. Because what happens is one of the two chlorines changes places with the hydrogen. And so you always end up with like an HCl when you're done. Or an HBr when you're done. So it actually always produces acid. So, any questions? Okay. I know I didn't leave you a ton of time. You guys have about 10 minutes today. Tomorrow we'll do our lab, and then I'm sure you'll have time to work on that quiz tomorrow too. So, sound good? Yeah, it's Monday. Okay.